So again, we mentioned in the abstract that we needed it's an extension. The Ramanujan's 1psi1 is an extension of the beta integral. So what do I mean by that? So first, let's see what is the Q extension of the gamma function. So this is quite easy actually. It's not as difficult as the usual gamma, the extension, the gamma integral. So first of all, you notice that 1 minus q raised per n is, this is what we have from high school. And we can have an extension of the n factorial as 1 into 1 plus q into 1 plus q square and so on up till 1 plus q plus so on up till q raised per n minus 1. So this is a very natural extension of the factorial function, q factorial function, if we take this as the q number. And then we write this as 1 minus q over 1 minus q times 1 minus q square over 1 minus q square, 1 minus q cubed over 1 minus q, sorry, 1 minus q. Sorry about that. And so on. 1 minus q raised per n over 1 minus q. And so this is qn 1 minus q raised per minus n. And using our definition, this is q raised per n plus 1 q infinity 1 minus q raised per minus n. So this is for a natural number, and now immediately we can think of defining gamma q of x plus x as q infinity over q raised per x q infinity and 1 minus q raised per minus x plus 1. So why do I want x? Because I would like gamma q of n plus 1 to be equal to n factorial q. So this is rather easy, and in fact this is there in Ramanujan's entries, this definition. And one can see immediately that gamma, one of the very important terms which almost define the gamma function is this. So one can see that gamma q of x plus 1 just by plugging it in here. This is minus x, and then it's almost immediate that you can just again multiply and divide by 1 minus q raised per x and absorb the 1 minus q raised per x here. So q raised per x q infinity, and again this is 1 minus q raised per x 1 minus q of gamma q of x. So this is a q analog of the gamma of x plus 1 equal to x gamma x, and one can see that one can prove, I won't prove it here, but one can prove that the limit as q goes to 1 of gamma q of x is actually equal to gamma of x. So the proof it's not so bad either. It extends Euler's limit definition of the gamma. So that's the q gamma function. So we have one of these two items. Let me give you the other extension, the q integral. So this is an idea which goes back to Wallace and Fermat. So so far we are, in time we are before Ramanujan always. Nothing which we have done is something modern. So that will come towards the end. So the integral, so what they did was they calculated the integral of x raised per k in 0, 1. And this is how they did it. Unfortunately, I haven't covered this in my calculus class, but I hope some students are here. So this is the interval, and what you do is what Fermat and Wallace did was that they made an infinite set of intervals here. So q raised per n and q raised per n plus 1, they made sum, a Riemann sum, or an area sum out of these. So this is y equal to x to the k, and again q in this case is between 0 and 1, and they make the infinite series. So the area is approximated by, so the difference between, this is the length of this guy, the height is q raised per n k. So this is y raised to x equal to n k, and then we are summing over all n. And this is not bad. This is equal to 1 minus q over, I mean, we can just sum it using the geometric series, q plus 1, k plus 1. So the integral of x to the t dt is the limit as n goes to infinity of this quantity. And that's 1 over k plus 1, as we know. So in general, that's a Q integral. That is Fermat and Wallace's approach, and that has been adopted by us. So in general, if f is continuous, then the integral from 0 to 1 ft, I'll call it dqt to represent this measure, is 1 minus q, n going from 0 to infinity, uh, f of q raised per n, q raised per n. So you can see there's a 1 minus q, there's a q raised per n and 1 minus q, which comes out over here, and q raised per nk, and the rest is from the option. So this is a q integral. This is the definition of the q integral, and we can define it from 0 to a, 0 to infinity in different ways. So, but this is the basic idea. So my claim is it's not 1 psi 1. Actually, the q binomial itself is a, so the q binomial theorem extends the beta integral. So what we do is, I'll just outline the steps. So take a going to q raised per y, and z going to q raised per x in the q binomial theorem. Okay, and we get q raised per x plus y, q infinity, q raised to the power x, q infinity is equal to summation n going from 0 to infinity, q raised per y, qn, and qn, and then q raised per kn. Okay, now take all these guys over here and write, use, aqn as aq infinity over aqn q infinity. All of these two guys over here, multiply and subtract, and you will get the following. So using this, one can simplify and get it to gamma q of, well, let me write an intermediate term first. 1 minus q, q raised per x plus y, q infinity, q infinity over q raised per x, q infinity, q raised per y, q infinity. This is equal to 1 minus q summation, and going from 0 to infinity, q raised power n plus 1 q infinity over q raised power y plus n q infinity. And there is a something here. Let me just write it here. Q raised power x minus 1 n and q raised power n. And this I write as a q integral 0 to 1 tq q infinity over tqy q infinity t raised power x minus 1 dqt. And this one I can write as gamma q of x, gamma q of y, gamma q of x plus y. So these two are equal, and as q goes to 1, this part by using our previous limit. So I just took a limit here in the q binomial theorem. Using this limit, we get, if q goes to 1, this goes to this integral t raised power x minus 1, 1 minus t raised power y minus 1 dt, and this goes to gamma x, gamma y, gamma x plus y. And this is valid for real x and y bigger than 0. So that's the famous beta integral which I mentioned. So far I've been meeting my targets. Just to summarize what we have done so far, so we began with the Jacobi triple product identity, and I will at some point show you that whatever we will end up with, Ramanujan's 1 psi 1, that actually generalizes this. And then we did the proof due to Ramanujan of the Q binomial theorem. And one of the things which came out was this limit. And then we had a Q extension of the gamma function and integral, and the claim was that that Ramanujan's the Q binomial theorem, not Ramanujan's, Cauchy's Q binomial theorem extends the beta integral. And now we are ready for Ramanujan's 1 psi 1. So, as I mentioned, this is an expression for this bilateral sum, and it's called 1 psi 1. It is denoted by this notation, and I should say that when this is a B here, when B is equal to Q, then we have a 1 phi 0. Okay, so this phi and C series, the phi series, as we saw, is the Q binomial theorem. So, so the meaning of the term 1 psi 1 comes from this hypergeometric notation, where you have R phi S series in general, and psi series come when they are bilateral, when there is no Q in the bottom. And this Q, I explained to you that when B is equal to Q, then it terminates naturally from below. So it's a very natural. And now the proof of this, it's actually a derivation come proof. And this proof is due to Murad Ismail. So I should mention that almost all the things that I'm doing are so far are taken from two sources. I mean, one source really. It's ASCII's lectures, and then those lectures have been sort of perfected into a book by Andrews, ASCII, and Roy. by on special functions. And this proof is of 1 psi 1 is folklore. It's by Murad Ismail, and uh, Murad is a collaborator of mine. We are friends, so I asked Murad how it happened, and he told me that he was, he used to attend ASCII seminar, so he was there from Canada. He was Walid Al Salam's student, and he would keep going and meeting ASCII and working with him and with that team. And they had a special function seminar there, and they were talking very excitedly about this result, 1 psi 1. So ASCII had a proof, Andrews had another proof. They both had written it up, and then Murad said that when um, he was going back to Canada in the plane, he found he thought of this proof, and then as he said, I hate you after hearing the proof. But they got it published, and then he says that it wasn't so neat and simple initially. It came out as a half-page proof eventually, but it was thanks to Andrews who edited it a lot and made it nice. So anyway, it's a nice derivation come proof, and here is the idea. So first of all, first, what we need to just use the ratio test to see that once this sum converges here, converges for uh, in this region, annulus. So this is easy. I'm not going to do it. And then you notice that when b equal to q raised per m, for m, some m bigger than 0, then the sum terminates naturally again. So he considered this sum a q n over q raised per m q n z raised per n, and now n is going from minus n plus 1 to infinity. Okay, and you can shift the index, so n is going from 0 to infinity, a q of n plus m minus m plus 1, and then q raised per m q n minus n plus 1, and z raised per n minus n plus 1. So what am I doing here? I'm saying that n equal to 0 here will give me this n equal to minus m plus 1 term. So and n equal to 1 will give me the second term here, minus m plus 2 and so on. And then I use this identity. This is true for all integers n and m. I just divide it by, I can just split the sum in some sense. For n and m positive, it's very easy to see, but otherwise it's just a ratio of infinite products. And then if I do that over here, then I'll get some guys outside. These do not depend on the sum. And this is n, and this is q, q, n, and there is a z term here also, z raised per n. And then this chap you've already found. So this chap we've already got, and it is by the Q binomial theorem. It is this guy aq minus n plus 1 times zq infinity and zq infinity. So we can evaluate this chap, and with the result, after some manipulations, one gets this sum over well, it was over n or m, forget. So it's naturally terminated. I'll just write it over n, aqn over q raised per m, q n, z raised per m. And this I can write, this whole business I can write in terms of as follows: q over az, q raised per m over a, az, q infinity. So this is just elementary algebra here. So when b equal to q raised per m, just by using the q binomial theorem, one can get this expression. And here is the proof. So now this is the theorem. For b by a less than z less than 1, we have n going from minus infinity to infinity, aqn over bqn. So I have discovered what it is, what it should be. I'll just replace the q raised per m's by b now. And the proof due to Ismail is as follows. The by this guy, by star, this result is true for all b equal to q raised per m. It's an analytic function. It is analytic in b as a variable around 0. I mean, we have the specific conditions, right? So for b less than az, it is analytic here. And this guy is true for m equal to 1, 2, 3, which has a limit point 0. So therefore, well, what should I say? It's done. So by analytic continuation, these two sides are equal. So this has been described as the proof from the book. So for the students here, the story is that Paul Erdős used to think that so he was not religious, but he would call God the supreme fascist. So he said the supreme fascist basically works in ways to keep some proofs from him. The proofs are in the book, and the point was to discover those proofs. Those were the perfect proofs, the most beautiful proofs. So this one has been described as a proof from the book. Okay, I suddenly see a lot of chat messages. Okay, well, all right. So so this is Ramanujan's one psi one. Let me highlight it. I mean, somebody like Hardy would probably not think, would think it's a nice, simple result. But the point is that he highlighted it, and mainly it was because it was a sort of, it was the way Ramanujan handled theta functions was an exciting thing, and this was one of the obvious results which went beyond Jacobi, Gauss, and so on. So let me just list a few corollaries. Um, so if we take b equal to 0 and z going to z over a, and then take the limit as a going to infinity. So this is called a confluence limits. It's called, physicists call it confluent limit. I don't know why. This process is called confluence. If you take z going to z4a and a going to infinity, then you get the Jacobi triple product identity, which was, if you remember, it was z q over z, and now I write the q over here. So you can see this term. If I replace b by 0, so this will disappear, and I place z by z over a and take limit as a going to infinity, this term will disappear, but it will leave some residue, and this is a residue. And I mean, not that residue, it's leave something, some terms behind. And there are further corollaries. I'll just take 2 minutes to write them down. Other classical corollaries which follow from Jacobi's work. So number one is due to Gauss, and this is, well, k here. So k going from minus infinity to infinity. It's q square infinity, and minus q square infinity square. This is Euler's pentagonal number theorem. This is the famous pentagonal number theorem. And then there is another one due to Gauss. So the Gauss's interest in sums of squares and in general quadratic k plus 1 over 2. And then Jacobi. So these are 4 classical results along with Jacobi triple product identity, which follow from Jacobi triple product identity. And you can see the interest of number theorists here. It's a generating function for k square, for squares, then pentagonal numbers, then triangular numbers. And again, some kind of triangular numbers, but with a with some kind of weight. And these are the classical theta functions in some sense. If you raise this to the 24th power and compare the coefficients, you get Ramanujan's tau function. So the interests of number theorists are right there in these kind of functions, and of course that is the reason why Ramanujan's one psi one seem to cause some comment. Okay, so I've reached the end of my presentation. Any questions or queries?
Very good talk.
Thank you, ma'am. Thank you.
And I put a question in the chat.
Okay, let me see here. There are binomial theorems of powers are replaced by
Like, x raised to n and y raised to m are replaced by p and x, p and y from an orthogonal polynomial system Pn.
Yeah.
And then it is an orthogonal polynomial system in x plus y.
Right.
And so these are called binomial theorems for orthogonal systems.
Yeah.
Now, you can even replace p and y by q, p and y by q and y from two. You can mix two orthogonal polynomial systems also, and
Right.
then there will be a third polynomial system in x plus y. So
Yeah.
what happens in your case? You remember you gave binomial theorem proved by Ramanujan, binomial within inverted commas.
Right.
So what will happen here for such situations?
I don't know. It's a good question.
Thank you.
Needs to be
Okay. Okay. And I might have sent you my chat tackling problems at Memphis conference. that has references to such binomial polynomials.
uh-huh.
Okay.
Yeah. Yeah.
Lots of papers by people.
Right.
They keep determining which class has binomial theorem, and
Right.
most of the classes have binomial theorem.
Right. So yeah, there is a famous theorem of Weierstrass, uh,
Ha
which talks about these additive. I mean, in general, you have a system where x plus y raised per n. I mean, some kind of additive like sine x plus y in
ha.
terms of sine x and cos x. So here's a general, very big class of theorem which says that all such types are basically either polynomials uh, periodic functions or elliptic functions.
Okay, and Ajay Shukla has worked in this too. And
So,
my paper on polynomial representation of quantum entanglement
uh,
in contemporary AMS 687
right,
uh, has has references to such binomial theorems also,
right.
because that gives me entangled vectors.
I see.
So two of my papers or talks have these things used already.
Right. So I'm just